Hi, Chris Good here, and this is a solution to these one-way ANOVA practice problems. The solutions actually appear in some other YouTube videos on the channel, but these have been updated because I'm going to solve this a little bit differently because I'm going to fill in this source table instead of listing these things out. Also, we're going to follow all four of our null hypothesis significance testing steps along the way to better resemble the way that the in-lab quizzes are going to go for this material. So let's take a look at this first problem. A research study was conducted to examine the clinical efficacy of a new antidepressant. Depressed patients were randomly assigned to one of three groups: a placebo, a group that got a low dose, and a group that got a moderate dose of the drug. After 4 weeks of treatment, the patients completed the Beck Depression Inventory. The higher the score, the more depressed the patient. The data presented below compute the appropriate test. Well, we've got three groups. We're going to end up with three means, and that means the appropriate test is the old analysis of variance. I've copied these into an Excel table. It's available on the course website. So let's go through here and talk about what we'll need to solve the problem. I'm going to go ahead and begin down here by entering our four steps. State the null hypothesis. We're going to set our alpha at 0.05, just like usual, and look up F crit. We're going to need degrees of freedom for that later. We'll compute F. We'll make a decision, and then we'll write our sentence. We'll go ahead and fill that in later on. All right. Step one, state the null hypothesis. We're going to compute three sample means here. We want to know if they're different from each other. So what we'll do then is imagine that these three means that we're going to compute came from identical populations. So mu for the placebo should equal mu for the low dose, should equal mu for the moderate dose in the population. That means there's no treatment effect. Let's go ahead and compute our sample means here. This is just equal average. I'm going to take the average of the 5 scores for the placebo group and copy and paste that. We have the same sample sizes in each group, so it's okay to do copy and paste here because this is just going to take the average of the 5 numbers above it, and so will this one too. If we had unequal ends, we'd want to make sure that we're taking the average of all the scores in a particular treatment group. We can't really do step 2 until we get our degrees of freedom, and in order to do that, we're going to need, oops, I didn't put K up here. Let's make a spot for K. All right. K is just the number of means that we have. You can count the means. I mean, you know, there's 3. You could just put 3. We also need the number of scores that we have. We do need to count these just so we don't make a mistake. It should be 15 scores, 5 in each of 3 groups. That's good. This is starting to look like the example we did in class, but it's not always going to look like this, so you want to double check your numbers. So we can compute degrees of freedom between treatments, which is equal to K minus 1. We can compute degrees of freedom for within treatments, which is equal to N minus K. And we can compute the total degrees of freedom 2 ways. We can add between and within, which should be 14, or we can say it's big N minus 1. It's the same number either way, but it's often good to double check just to make sure you're on the right track. So now we need to look up a critical value for an F with 2 and 12 degrees of freedom. So I'm going to go down here to my F table, bring this into the view for you guys. Zoom in. Remember that in the light face type, we're looking at 0.05, and in the bold face type, it's 0.01. We're using 0.05 like usual. So for 2 degrees of freedom in the numerator, because that's between treatments, and for 12 degrees of freedom in the denominator, because that's within treatments, we're going to use 3.88. I know that's the same critical value we used in class, but it's not always going to be that. Make sure you can look up the proper F crit. 3.88 is F crit. Now we got to start computing F. We could start anywhere. I'm going to go ahead and start with between treatments sums of squares. In order to do that, we need t squared over n and g squared over big N. So let's do our t's first. It's just the sum of all the scores in each group. First, the placebo group gets a t. Because we have the same sample size, we can just paste that sum formula into the low dose T column and row. And we'll do the same thing for the moderate dose. You'd want to sum all the scores you have in a group though, so make sure in the event that you don't have equal n's. Ooh, speaking of n, let's do n. That's just the number of scores that you have in one particular group. That's what little n is. And because we have the same sample size, we can do that. Copy and paste. But make sure that you're counting all the scores in a particular group. We are this time, because it's nice and even. Let's square these t's. That's equal to this t raised to the second power. Same here, same here. There's your t-squares. Don't get afraid of big numbers. These are large numbers up here. When you start adding stuff and squaring things, you're going to get some big numbers. Don't worry about it. You're on the right track. We're going to need g. That's the sum of all the scores. Make sure you highlight all the scores. Might be difficult to do if you have unequal groups. And then g squared is just the square of that number, g. Great. I think we've got everything we need to get between treatments sums of squares, which is the sum of our t squared over n, which we haven't computed yet, all right? And then you subtract this quantity, g squared over big N. Now we're not going to get a value here because I haven't computed t squared over n yet. I forgot to do that. But if I enter this, I know it's giving me a crazy number. It's a negative number. That's really weird. It's because we subtracted g squared over n from nothing. But as we fill in these numbers, so that equals t squared over n, copy and paste, you'll see that that formula updates. Might want to calm down on the decimals here. I'm going to just reduce that number of decimals. Okay. And that's our between treatment sums of squares. Yeah, that's right. We could go ahead and get mean square. I'm going to hold off on that just for now. I want to get within treatments sum of squares. That means we got to get sums of squares for each group. So I'm just going to copy these labels over here and note that I'm doing deviations. So for the placebo deviations, I want to take a placebo score and subtract the placebo mean, holding that mean constant, so that when I copy and paste it into this column, I'm getting deviations from the same mean, 38.2. You can't paste it into here because you want to subtract from the low dose score the low dose mean. Hold that constant, copy and paste, and we'll do the same thing for the moderate dose. Moderate dose score minus the moderate dose mean. Hold that mean constant. Oopsies. And there we've got deviations. Let's square those. Just by saying, hey, square, not that number, square this number, the placebo deviation. We can paste it all the way down here, but because we're squaring, right, same operation on all these numbers, we just paste it all the way for all of them. Now we've got squared deviations within each treatment from their respective means. And sum of squares within treatments is just the sum of those squared deviations. Awesome. Total sums of squares should equal this, the sum of those two things. Mean square should equal sum of squares over the appropriate degrees of freedom. So mean square between treatments is sum of squares between treatments divided by degrees of freedom between treatments. And if you copy and paste this, what you'll get is sum of squares between within treatments divided by degrees of freedom within treatments. Now we can get our F, mean square between treatments divided by mean square within treatments, 11.27. And that's beyond our critical value of 3.88, and so we'll make our decision to reject the null hypothesis. And what can we conclude from that? Well, we'll get to this in class, but that doesn't mean that people in the placebo group had higher depression scores than people in the moderate dose group. You actually don't know that. All that you know is that the null hypothesis isn't true, that one of these population means is different from at least one other one. So you can say that the drug treatment had a significant effect on depression score with F at 2 and 12 degrees of freedom equal to 11.27 and P less than 0.05. But what's the direction of the difference? I'm always telling you guys you need the direction of the difference. Well, we don't know that yet. We have to do another test to figure that out, and the one we're going to use is called Tukey's HSD, the honestly significant difference. And we're going to talk about how to do this in class. The formula for it is Q times the square root of mean square within divided by n, little n, and you can only use this when you have the same number in each group. And we do in this case, so we can use Tukey's. But what's Q? Well, we need to look up Q in the Q table. I've attached a Q table to this F table. The Q table is a little bit different. Q is called the studentized range statistic. That's what Q is. And you look it up kind of like you look up critical values for F, but it's not exactly the same. The columns here are not degrees of freedom between treatments. It's the number of treatments you have. So don't get confused when you're looking up Q's and F's. We have 3 treatments, so we're going to be looking in this column. Same deal. Ooh, getting a little storm here. That's exciting. Okay, so if we get 3 treatments, and we have 12 degrees of freedom in the error term, remember, because the error term is the denominator. With 3 and treatments and 12 degrees of freedom within treatments, 3.77 is the value for the studentized range statistic. And I'll show you an example of that in class. It's not going to be a big deal. So Q equals 3.77, and HSD is equal to Q times the square root of this quantity, mean squared within treatments, not that one, but this one, mean squared within treatments, divided by n, and you can pick whichever n that you want. It just pick one of them. They've got to be the same to use this, and we'll pick n. That's 5, or you could just type 5. Okay, so the honestly significant difference is about 13.7. What does that mean? This is how far apart 2 sample means have to be in order to be significant. We've got 3 sample means, so the question is 20.6 more than 13.7 away from 38.2? Right? Let's try to do this by column. So we'll do placebo versus low dose. That's equal to the placebo mean minus the low dose mean. That's 17.6. It's bigger than the honestly significant difference, so that one's significant. We're going to put an asterisk there. How about placebo versus moderate dose? That's equal to 38.2 minus 14.8. 23.4. Okay, so that's a significant difference. We've got one more comparison to make, low versus moderate dose. Maybe you're thinking to yourself, hey, you told us you couldn't do multiple comparisons because of the risk of type 1 error, which is true, but Tukey's HSD actually takes this into account. And we're not actually inflating the risk of type 1 error. Plus, we already found that we had a significant effect, so it's okay to do this test after the fact. In fact, that's what we call this type of test. We call it a post hoc test, and that means after the fact. So low versus moderate, 20.6 minus 14.8. I don't think that's going to be greater than 13.7. It's not. It's 5.8. So no asterisk for you, buddy. What can we conclude from this? Well, it's time to write another, yes, a second sentence. So we're going to say post hoc testing using Tukey's HSD revealed. That's a great way to start your sentence talking about post hoc testing. That depression was significantly lower on the low and moderate dose of the drug than on placebo. And we're just going to report HSD equals 13.69 and P is less than 0.05. How do we know it's less than 0.05? Because that's the level of significance that we used in the Q table. And that is it for problem 1.